Okay, before we wrap up this section, we want to talk about a special type of series called the binomial series, and we're even going to look at the Maclaurin version of the binomial series. And then the last two examples after we discuss binomial series, we'll go to that Maclaurin series handout. Okay, so the binomial series. The binomial series is f of x in this form, or 1 plus x raised to the k. All right, so the only requirements on k is that it is an integer. It could be positive or negative. All right, if we are centering at 0, which we need to do for the binomial series, then let's just explore what the Taylor series would say. So let's take several derivatives and let's plug in 0. Okay. So in the same style as the previous question, so I've got the original function, plugging 0 in, well, that'd be just 1 to the k, right? So that would be 1 for, wouldn't matter what the value of k. If I take a derivative, whatever the value of k, I'd multiply it down, I'd subtract 1, right? So plugging 0 in for x, well, that would just be k. If I was to take a second derivative, now we can really start to see the pattern happening over here. Another derivative, well, I would multiply the k minus 1 down, and it would drop to the k minus 2. Plugging in 0 for x, well, that is all just going to be 1, so I've got k times k minus 1. The third derivative, and we really see the pattern clearly at this point, multiply the k minus 2 down, it drops to k minus 3, but then plugging in 0, well, all of this part goes to 1, k times k minus 1 times k minus 2. And you can see, oh, okay, it starts at 1 and then k, and then we keep attaching that next part that we multiply by each time. All right, so let's use this idea for this example right here. Find the Maclaurin series for 1 over 1 plus x squared. Okay, now we know we're centering at 0 because it's a Maclaurin series. And we can recognize that as a binomial series if we think of it as 1 plus x to the negative 2. So we can identify the value of k. All right. So if we wanted to know, the numerators of our coefficients in the power series, we say, hey, that's a binomial series. So I know the original function at 0 is always going to be 1. The first derivative at 0 is always the value of k. I wish I could keep this all on the screen at the same time. The second derivative is k times k minus 1. So here that's negative 2 times negative 3. And let's stop at the third derivative. Negative 2 times negative 3 times negative 4, negative 24. So we've got 1, negative 2, 6, negative 24 by following our pattern here for the k's. And I think at the third derivative, oh, I went ahead and did a fourth derivative. Hey, why not? Negative 2 times negative 3 times negative 4 times negative 5. Keep subtracting 1 each time you attach another number. That is positive 120. Right, looks like I continued at the top of the next page. And at this point, I just went ahead and filled in those numerators, right? You can even say, like, we'll get our formula back up here. So 0th derivative, we've got our numerator 1. It's over 0 factorial, and we raise to the 0 power, so it's just that number. The second numerator is -2 over 1 factorial, and we raise to the first. Remember, this is a Maclaurin series. We're centering at 0, so think of that as x minus 0. Then the next one, well, for our particular function, we've got 6 and 2 factorial squared, then -24, 3 factorial to the third, positive 120 over 4 factorial x to the fourth. And there you go. Now these clean up very nicely. 2 over 1, 6 over 2, 24 over 6, 120 over 24. And I think I missed that this is actually a minus. 1 minus 2x plus 3x squared minus 4x to the third plus 5x to the fourth. Okay, minus dot dot dot. So if I was asking you just for maybe the first several non-zero terms, you could stop right there. But what if I was asking you for the pattern? Let's go ahead and see that. Since everything here, nothing's really too crazy once you get used to noticing these patterns. So first thing you notice, it's alternating, positive, negative, positive, negative. It starts with a positive, so that's simply -1 to the n if we start at 0. The values of the exponents on x, it's as simple as x to the n, 0 power, first, second, third, fourth. Here it really is probably preferred to start at 0, especially for those powers of n. Then what about the 1, 2, 3, 4, 5? Well, at 0 it's 1, at 1 it's 2, at 2 it's 3. Okay, always add 1 to your value of n, and you'll have that pattern. Again, I'm saying, oh, it's not too bad, and you might disagree. Relative to what this could have been, it's not too bad. Doesn't mean it's going to come immediately. That's not what I mean. Oh, it's so obvious. No, that's not what I'm saying. It takes some thought. It takes some guess and check. It takes some practice with these, getting used to these patterns. But compared to what, other situations, this, okay. At this point, go ahead and take a look at that Maclaurin series for elementary functions, okay? I've got my copy right here also. This one. Hey, it all fits on the screen. That is incredible. I was not expecting that. So at this point, if we were in class, I would hand this out here and we kind of reflect on it a little bit. So it's pretty nifty. They're all Maclaurin series. We're keeping it as simple as possible. This is almost like a table of integrals in a sense for these. How many are there? 1, 2, 3, 4, 5, 6, 7 functions. Okay. So you notice it begins with the geometric series. So that was the entire focus back in 11.9, with some details changed. The geometric series, well, here a is 1. So it's just n equals 0 to infinity, x to the n, and you see several expanded terms there also. E to the x, we explored e to the x back at the beginning of the whole discussion on 11.8. And we realized through a lot of several minutes of work that it was n equals 0 to infinity, x to the n over n factorial. But we're not going to reprove that here. We did it back there, but here's a few terms if you expand. Okay, it's like, how simple is it? X to the n over n factorial for values of x that converge anyway. Though that's an approximation. It's equal if you've got infinitely many terms. Okay, we saw sine x a few minutes ago, although when we looked at sine x, we were centering at c equals pi over 4. So this is assuming you're centering at 0. And there it is. Now that's getting a little bit harder, right? It's alternating x to the 2n plus 1 over 2n plus 1 factorial. But then when you look at the expanded form, you're like, oh no, it's actually pretty simple. X to the first, and we just got the odd powers of x, and we're only doing the odd factorials. And then it's alternating. Interesting. Cosine, very similar, except it's the evens. The 0, 2, 4, 6, alternating as well. Really cool. Turns out we have arctangent. Okay. All right. And that's kind of got a similar thing going as sine, except it's not factorials in the bottom. Natural log of 1 plus x. Let me raise this up a little bit. Natural log 1 plus x. Notice that we start at n equals 1. So that's something different, because we end up dividing by n here, so we don't want to divide by 0. But all it is, x to the n over n, it's alternating, and we have n minus 1 since we're starting there because we want to begin positive. But even that's very simple, very similar to arctangent, except we're not skipping, we're not just doing the odds, we're doing them all. And finally, you've got the binomial. Well, we did that just a moment ago. You see this notation here for k choose n. You may have seen that in a previous math course at some point. I'm not going to go into where that is. This is what we know it to be, right? The coefficients are 0. Or excuse me, what are the coefficients? The 0 term is 1, and then k times k minus 1. Okay, yeah. All right. So what kind of questions are we going to use with this sort of thing? We're going to look at 2 of them. What if we did a small adjustment to some of the things that we see in that list? So what if we wanted the Maclaurin series representation of f of x equals e raised to the square root x? Like, okay, well, I mean, I've got the representation for e to the x. How do we get e to the square root x? It couldn't be simpler. All we got to do, we'll use that e to the x form. We'll just replace x with square root x, or maybe you prefer to replace it with x to the 1/2. That's it. It's just a substitution. So here it is. I prefer it in this style. They've got e to the x as x to the n over n factorial. I kind of like to put that x to the n to the side. But the idea is replace the x with square root x, or x to the 1/2. That's it. X to the 1/2 is nice here because then we can simplify and get that. Done. That is pretty awesome. Hey, I like this Maclaurin series, this list. Let's do one more. Now this one will have a little bit more going on to it. Well, maybe just in a different sense. Let me get rid of this. All right, how about f of x equals x squared arctangent x? Hey, we've got the power Maclaurin series for arctangent x there. Here we have the x squared. Hey, all we got to do couldn't be any simpler. We're just going to multiply the power series for arctangent x, multiply it by x squared. That's it. That's all there is to it. Now, we do want to simplify. How can this be simplified? Well, let's put the x squared in there and combine it with this other x. Also, you notice I wrote this a little bit differently than the way it is that the textbook presents it. I kind of like, numerator there, the x to the side. That's my thing. Textbook doesn't, kind of mixes things up a little bit. Okay, so I'm going to push this x squared in there. And when I put it inside, it's going to combine with this one. Well, I'm just going to add the exponents. So now I've got 2n plus 3, the other parts stay the same. And there we have the Maclaurin series representation for x squared arctangent x. Of course, keep in mind this is only for values of x that would cause our series to converge. But the functions are exactly equal when you have infinitely many terms. That is the end of 11.10. Go check out homework. See you in the live session.